Thanks for joining. My name is Arsha Judani. I am the director of a research lab called Human-Robot Interfaces and Interaction at the Italian Institute of Technology. We are located in Genova, Italy. We are a research group that work on various robotics, human-robot interaction, and machine learning applied to robotics scenarios. But today I'm going to talk about a project that I coordinated, which was ended recently. The project is called SOPHIA, and SOPHIA stands for Socio-Physical Interaction Skills for Cooperative Human-Robot Systems in Agile Production. So I had the pleasure of working with several academic and industrialization, acceptability, and industrial partners. IIT with me was the coordinator. We had University of with VUB from Brussels, we had Montpellier, and we had University of Pisa, INAIL, and BAO as governmental bodies for occupational health and safety were involved, and DIN, the standardization policy making body of Germany, was part of this consortium. And we had some important industrial key players such as IMK, Hydria, Volkswagen, and Handcam Kiers. So what we did in SOPHIA was trying to respond to some challenges that most of you are aware. Obviously, everybody talks about robots replacing humans, but this is what media is trying to push. Obviously, the problem is not really the actual, let's say, taking over of the robots, but actually the workers that are missing. So the aging workforce at the moment is advancing, which means that we have more people today leaving the workforce than joining, right? So it's estimated that by 2030, we have about 85 million people, which is a huge number to have this gap, and their positions in industry will not be filled. We are facing a very dramatic skilled labor shortage. Obviously, when these people move out, they take with them all the skills and all the know-how. And this is this will create a big crisis for industry. Today, we are suffering a lot from bad working habits, especially the ones that are connected to physical working habits, like causing work-related musculoskeletal disorders, or the ones that cause mental disorders related to work because of anxiety, stress, and all that. And they're causing a lot of lost in terms of productivity coming from absenteeism or diseases for today's and tomorrow's workers. Numbers are very dramatic: 240 billion euros per year for physical aspects, and almost triple of that for the mental aspects. Obviously, everybody also knows about production flexibility, which is needed, and mass customization, which is today's struggles. So SOPHIA's approach was mostly technical. Of course, we worked on a lot of core components for robotics and AI algorithms. We looked into making modular robotic systems. We worked on estimation algorithms, and we worked on new methods to anticipate human factors. And they were actually providing some quantitative evaluation of human physical states and psychological states at work. Then we started using artificial cognition to understand how physical systems and humans can cooperate and interact in the best possible way, which is not pushed, but mostly intuitive and natural. Then we built in parallel some robotic assistants I will tell a little bit about that and of different morphologies and different use. This was mostly how it was built. We had components, technological components interacting with each other. Then in parallel, we had acceptability assessment and standardization, because we wanted to see if some of these outputs of the project can be standardized to contribute to better, let's say, defining what is needed and how things should be done in terms of occupational health and safety and robotics in future. So for us, acceptability, performance, and standardization also created an observatory, let's say, overarching kind of component, which looked at to monitoring, warning, and acting, the three main principles of the SOPHIA project to foresee their developments. So now let me give you some highlights of technical work and technical developments we've been doing. So one of the main components that we worked on in SOPHIA was new ergonomic monitoring tools. So these tools ranged from offline pre-processing, tools which in collaboration with IMK, IMK Ergonomics in Germany. We built some tools that the current working states could be simulated, and all the ergonomics and human factors can be evaluated in an offline manner to understand where are the issues, right? So this was a simulation. This would give you KPI analysis. You could just quickly reconfigure the setup, and this was mostly based on industrial ergonomic models that was and is available today to have a very quick understanding of what is wrong. This would give you some really nice and precise KPI analysis about productivity as well as ergonomics, like what are the cycle times and all the stuff that was happening, how much walk path cycles are, and things like that. Then we went towards online techniques, but still somewhere in the middle, that they were mostly data driven. So we started collecting a lot of data together with email in different experimentations, and we analyzed all this data in depth. A lot of sensors we used. We did better KPI evaluations, and we tested different classical and machine learning algorithms to understand what is causing bad ergonomics and what are the issues and what are the signals can be used for that. We create a really nice interface, and we actually it's an instrumental base to include multi-sensory information for ergonomics tracking. Then obviously we also moved towards more online. So this was online, let's say, methods in collaboration IIT did with the University of Twente. We built techniques that go way beyond the state of the art and tell you in real time how human factors are moving, are changing based, for instance, the compressive forces, torques of the human body, and how things can be monitored. This is really useful, especially when you're in direct connection with robots or assistive devices, to be able to control their behaviors in real time. SOPHIA cobots ranged from agile, interactive, let's say mobile basis, to more high payload capacity. So on the left side, we customized some solutions and built our MoCA system, and then we built our own components with the arm, which was up to 20 kilogram payload capacity, which back then was extremely new, a torque controlled robot with 20 kilogram payload. Then we made our platforms interactive. As you can see here, robots could feel also in their bases using artificial skins. The robots were controlled in whole body, so anywhere you would interact with them, the robot would respond. And this was extended to this our SOPHIA platform that was a group at IIT, humanoids and human-centered mechatronics, that I collaborated with them to build and design and test these facilities. This platform, which you can see how nicely can also easily move around with such a high load capacity. SOPHIA have concentrated a lot on human-robot interaction. This is some work with the VUB, robot reconfiguring based on the configuration, based on the ergonomics status of the person. If people were starting to develop some fatigue, the robot was reconfiguring on the fly and helping the worker to do some better tasks. Then we started looking into cognitive ergonomics. In this particular video with the green background, you see the robot is monitoring the cognitive engagement of a person. If the cognitive engagement is too small and the rest is detected, so the controller pushes on productivity, increases the performance, increases the velocity, uses the collaborative effort, until it arrives to a limit, basically, which is the right spot when the person is engaged nicely, but not too much. Here, the robot intentionally pushed a bit forward, and the robot sees some stress, and it pushes back on the speed to align with the person's cognitive and mental capacity. Then we built some really nice interfaces to make collaborative robots work like exoskeletons without really have to wear them, and with much higher payloads. You can see some videos on the right side. No needing to wear any system. You could carry really heavy objects. So the payload of this robot was 16 kilograms. Move it around and as well perform such tasks with just a few newtons of interaction. In SOPHIA, we built different variable systems as well. On the left side, you see an elbow exoskeleton we developed in my lab. We used in industrial applications for pick and place, light pick and place. there in that room, there was no possibility to include robots because it was really tight. So exoskeletons were the best choice to avoid fatigue. In IIT, with HHCM lab, we also built a knee exoskeleton based on really new principles of actuation, which this is the first one knee, and we recently also built a whole body lower exoskeleton. So as you see, the shoes also, they have sensors that they can measure ground reaction forces and the center of pressures. Together with University of Pisa, we built the supernumerary arms that was called Soft Hand X2. You can see these supernumerary arms could keep and hold the objects, the space where you could be working on them. On the top side, you see the drilling, which it was meant to reduce the basically the vibrations and stuff like that. As you know, the vibration transmission is really dramatic for workers, especially the ones that work 8 hours per day and several days per week. SOPHIA wearables included systems that provided feedback about bad working conditions. In IIT, my team, we worked with ErgoTag. ErgoTag is just a wearable system that vibrates and gives you some direction about what posture you should pick, given the task constraints, which is the most ergonomic. In University of Pisa, we built a pressure cuff. As you can see, it was two-dimensional, was squeezing and also giving some motion, not only giving some ideas about the pressure, but also some directionality was embedded in this nice mechanical design. In University of Twente, we built a soft suit, what's kind of both assistive and let's say helpful to arrive to better postures. And these were the SOPHIA variables that we use in our setup. SOPHIA also included a lot of data sets and simulation tools. They're still available, several vision data sets you can find, the industrial work and pick and place, tool use, and these are also good for training your machine learning algorithms. We also built a simulation environment that basically a collaborative human robot setting can be placed there. Just to give you some overall ideas about how the pilots look like. This is HandCam gears in the Netherlands. We first, as I mentioned to you, we analyzed in simulations how the work was done and what's the best way of actually interacting with bringing the robot into this. It was a gear loading and offloading system. This is a deburring machine. Everything was done manually. So we started looking into what are the challenges here and how eventually the robot could go. Then, as I was mentioning to you, we did some really tight analysis of movements, dynamics, EMGs, and everything to see what is happening. And then we came up with some solutions. This is the SOPHIA solution that gives you a really intuitive interface to carry 8 to 10 kilogram objects, or to teach to a robot how to carry these. This is an end effector we built in SOPHIA. How nicely you can see that a person can move it around and let me see if I can move a little bit further. Yeah. Oh no, it's fine. So to push it back, to put it forward, and the robot was automatically able to execute this. So here in this particular task, you can see that a gear is picked. I don't know how to move forward, but yeah, it's okay. With our, we call it MochaMan or Superman interface, which makes any robot of mobile base to act like a supernumerary limb. Some better close-ups. I just wanted to show you the final step of the robot, which goes and loads the tool that you see here inside the deburring machine. So here a person takes the gear that's supposed to be deburred, but yeah, then the robot navigates on its own and places into this deburring machine. So we worked also on making this autonomous, obviously, and however, I don't have a video of that right now, but you can see simply how nicely this whole task can be done in a really light collaboration between a person and the robot. Here, Mattia is clicking something, says, "Okay, I got this," and takes this interface with him because it's all personal interface, and the robot starts navigating and taking the object towards the thing. The robot has lidars and cameras in front, so all the mapping and navigation, everything is done autonomously. If a person passes in front, the robot is aware of collisions. If there are environmental changes, the robot maps in real time. You can see the space is cluttered because here the robot could not go directly in because there was this thing, and the robot decided to do this type of navigation. And here, basically, the robot extends the arm and eventually puts that thing into the gear thing, and then the task starts. Then we went to Hydria. Hydria, they had one task. They're in Slovenia. They let's say when these components came up the oven, a person should have hit them several times to make sure that these components detach. So we made some simulations to see how robots can help, because this impact was causing a lot of let's say issues in arm and the muscles, because it was causing some really reflection of impact on the joints. We designed several technologies for that. One was to use, as I mentioned to you, our exoskeleton for light pick and place. But for this particular task, we used a robot that they had available. And the good thing is here, the velocity of the robot was changing based on the cognitive load of a person. And so if the person was faster, the robot would move faster. If the person was slower, the robot would respond to that. And the robot was actually doing this hitting task, and not the person to avoid basically those issues. In Volkswagen, our task was to semi-automate this manual task. This is a turbo engine component that everything was done manually. Then we thought maybe this co-manipulation can be done. The robot brings this piece into the most ergonomic configuration for a person. And together with VUB, we built a really nice interface that shows the different phases of the task, and we can actually communicate with the robot. And the robot actually was picking the components from the bin and bringing it closer to the person and showing what's the next interaction that the person should do to avoid errors and mistakes. So this was really, really cool that we implemented inside our robot. So apart from all the technical work, we did a lot of interviews before, during, and after the integration of the technologies. We had almost 1,000 workers across Europe interviewed. And we really wanted to make sure that these technologies that we're developing are acceptable and compatible with today's workforce. And this was we did some code design actually with them, and we did a lot of integrations of their feedback into the design approaches. And this was really crucial for us to be able to develop something that eventually will be used by people. One thing that we are very proud of also is our contribution to standardization. We did a SEN workshop agreement on guidelines for introducing and implementing real-time instrumental-based tools for biomechanical risk assessment. Here you can see some information if you want to take some notes. This was a work of 3-4 years in collaboration with DIN from Germany. We did a lot of meetings with the ISO, with groups, and then finally we came up with really nice contribution. This is a very long document, and we're providing a lot of insights on this topic. So we were glad we had SOPHIA ended with a lot of achievements. We had more than 100 publications, 12 innovations, a lot of PhD theses, a lot of invited talks and contributions basically across Europe. And I'm really grateful for all the work that the partners did in this project, which its effects and impacts are still continuing. We outreached in several, let's say, events, from TV to, let's say, this was a Europe Parliament. I was invited to industrial settings. Here, actually, the President of Europe visited some of the technologies and made a tweet about it, and you can see the SOPHIA logo in the back, which was really, really important for us. So these are the SOPHIA impacts. In the end, we created a modular and reusable core technologies that we wanted to actually be able to reassemble them in a sense and use for different issues. In fact, we had a healthcare use case, and we use some of these technologies to show that how these technologies can be applied to different use cases, not only the ones that we focused in this project. Social sustainability was for us was really important to keep humans in the loop and make sure that they're contributing to the success of this. So if you want to hear some of the experience from the CEO of HandCamp, he made some really good remarks about how these technologies were evolved and how these can be used. You can just simply scan this QR code and it will take you right away to this YouTube basically interview with CEO. He's a brilliant person, very open to changes, which is sometimes rare in industrial environments, and I had the pleasure of working with him. Okay, this is it. I would like to thank you very much. I hope, I didn't go too far with respect to our time. This is the consortium. We had the kickoff meeting some years ago, and thank you very much. I look forward to our interaction maybe in 40 minutes from now. Thank you.
Thank you so much, Arash, and thank you for this insightful presentation. It's really impressive to see how the project puts human well-being and ergonomics at the very center of industrial productivity. So thank you so much. Now we move to Roberto Meatini from the University of Bologna, and he will be representing the IntelliMan project. Antonio, the floor is yours.
Okay, hello. Thank you very much. I'm going to share my screen. Okay. So okay, I suppose you can hear me and see the presentation well.
Perfect.
So good. Thank you. So, good morning, everyone. I'm Roberto Mettini. I'm an assistant professor at the University of Bologna, and I'm here today to talk about the IntelliMan project. Okay, so the IntelliMan in the short form stands for intelligent manipulation, and in the extended form, for AI-powered manipulation system for advanced robotic service, manufacturing, and prosthetics. So already starting from this title, we can see how the project is focused on developing solutions that are cross scenarios, leveraging on AI-based solutions. Okay. So let me give you some details of the project. So the IntelliMan project is a 42 months project. It's funded, of course, within the Horizon Europe framework. It is coordinated by our group at the University of Bologna, and in particular by Professor Gianluca Palli, which is the principal investigator of the project. The project started 3.5 years ago, and tried to ask a question. How to apply artificial intelligence to robotic manipulation, how to make robots learn purposeful, high performance, and safe manipulation tasks. So the motivation of these questions comes from a series of considerations that I would like to briefly outline. So in order to make robots physically interact with real world, we need manipulation. But to deal with the, let's say, infinite variations and series of uncertainties of real-world scenarios, we need to learn the manipulation task and make this process as shorter as possible. And this can be made by transferring skills that are already available to the robots. And of course, we want to ensure that the robot can interpret the external world, including both objects and human operators, and can guarantee safety. So in this scenario, the challenge, let's say, is to develop a multi-domain AI-powered robotic manipulation platform endowed with persistent learning capabilities in order to extract essential features of the world, plan efficiently the execution of the tasks, and particularly ask for new knowledge when this is necessary to improve the performances. To face these challenges, We have built a consortium of 13 partners, including universities, research centers, and companies around Europe. So within this ambition of developing AI-based manipulation solutions that can be used indeed across different application scenarios, we based on the challenge of requiring generalization among the task structures. And also we aim at exploiting shared autonomy methods in your robot interaction, combining both model-based and model-free paradigms, and ensuring failure detection and safety guarantees. And specifically, 4 use cases representing quite different application scenarios are targeted in the project. Let me mention these 4 use cases. So we have the use case related to upper limb prosthetics, in which advanced human-robot interfaces are pushed a lot, developing shared autonomy methods, and this use case is led by the INAIL Prosthetics Center. Then we have household aid robots for kitchen activities, in which manipulation planning and grasping of movable parts and grasping in clutter environments are the context-specific challenges, and this is led by the research center EURECAT. Then we have the robotic manipulation of fresh food, in which AI-based methods are specifically used also for the design of the gripper, which are investigated in order to handle these very fragile objects, and this is led by the company Ocado. And then we have the use case in the field of industrial manufacturing. And in particular, this is related to the robotization of wiring tasks, especially exploiting machine vision and deep learning to allow manipulation of deformable objects like cables. Okay. So now let me go through a sequence of AI methods that have been developed in the project, such that to give you an idea of the multiple directions from which we are facing the challenges that I have introduced. So I'd like to start from the usage of incremental learning paradigms to develop adaptive human-robot interfaces. These developments are mainly applied to the control of prosthesis that have been implemented and studied involving both groups of intact subjects and people with amputations. And basically, this approach allowed those interfaces to adapt a long time to the user's intent and to the master signals, while performing, of course, different end motions and grasps. So as you can see, for example, for these graphs that I'm showing, what happens a long time is that we can appreciate some learning curve about the improvement of human-robot coadaptation. But in addition to adaptive interfaces, we want to make also human-robot interaction efficient by means of shared autonomy approaches. In this case, a probabilistic machine learning tool, which is known very well with the name of hidden Markov model, is used to discover and learn structures and hierarchy in the human-in-the-loop control of robot hands. Okay, so the goal is to balance the level of autonomy between the user and the robot, and in particular to allow a fine grip force regulation during object grasping, which nowadays is one of the main challenges in human-in-the-loop control of robot hands and prosthesis. Of course, an approach like this will also require the development of advanced tactile sensors, which is an activity that is also carried out within the IntelliMan project. In particular, developing tactile sensors such as tactile pads for robotic grippers, but also piezoelectric skins for anthropomorphic robot hands that can cover the surface of fingers and palm and provide high bandwidth tactile signals. So All these developments in the project have been then also tested in virtual reality environments. This is very useful because allowed us to simulate human-robot interfacing and also to perform very interesting psychological studies. For example, in the videos that you are seeing, especially the one on the right, the user is performing some manipulation task, controlling the prosthesis, while some sounds signals are provided to the user. And in particular, these sounds are provided with artificially injected delays. And the way the user can perceive these delays during the task allows us to measure a metrics about the sense of agency and embodiment of the robotic devices. And very interestingly, we were able to transfer these type of psychological metrics from the prosthetic case also to industrial scenarios. Indeed, the development of advanced human-robot interfaces and shared autonomy methods within the projects have been applied also in industrial robotics scenarios. So, for example, one of the applications was to develop intuitive programming methods of both trajectories and grasping actions to manipulate and program the tasks involving both rigid objects and also deformable objects like cables, also using physiological signals and cutaneous feedback to the user, which is integrated in the loop of programming the robot. But the grasping itself needs also some more advanced abstraction, okay? In order to generalize the grasping for different objects. And to this purpose, in the project, we have investigated advanced geometrical description of robot manipulation in combination with AI methods. Let me mention, for example, this method, which is known under the name of sign distance fields, that allow to model articulated chains like robot manipulators in a very useful manner. And this will allow the generalization among different manipulation tasks like collision avoidance, whole body manipulation, and also very importantly to learn some generalization policy that allow the grasp to be performed on one particular object and then extend it on a class of somehow similar but different objects, as can happen, for example, in a kitchen scenario in which you want to, for example, set the tables for the breakfast or for having some lunch or dinner, and for other tasks like load and unload the dishwasher, which are tasks explicitly targeted within the project use case. Then, of course, to improve grasping skills, we will require also the improvement of the mechanical design of the grippers. In the project, we have developed the AI-based method to optimize this kind of design process. And this has been particularly exploited for the use case of the handling of fruits and vegetables, for which we have investigated innovative constriction and hybrid clippers in order to improve this very particular type of grasps with those objects that are very fragile, and also they are typically provided in a dense grasping scenario. While finally, in the industrial manufacturing, we have developed multiple solutions that are combining both computer vision and deep learning, also providing interface and interaction with human for the robotization of wiring tasks. For example, related to the placement of cables in collectors and channels or switch gears, we have developed vision systems in order to understand and perceive the environment to perform these tasks. Then we have also studied and developed the usage of large language models in order to allow experienced operators to command robots just by talking with them. And also probabilistic models in order to track connectors orientation by using, for example, very cheap setups like single camera, with the goal of performing alignments of very small parts to complete assembly tasks. So, in conclusion, now we are approaching the very last phase of the project, and in a few months the project will end. So what we are doing in this last period of the project is to build the final demonstrators, which will embed the functionalities that are coming from pushing more and more on integrating the different developed solutions among the different use cases and scenarios. Okay, so what we will present at the end is the results of these cross contaminations that we have had the opportunity to exploit in the project scenario and in the AI-based solutions that we have developed. So I would like to thank you for your attention, and I will be happy to participate to the interaction.
Thank you so much, Roberto. That was indeed a clear look into the complexity of shared autonomy, and I think that the way that IntelliMan handles the interaction in real time is truly a real game changer. So thank you so much. So now let's move on the last presentation of case studies to see how these intelligent systems are applied to large-scale industrial tasks. So I welcome our final speaker, Apostolis Papavarizeu, who is senior researcher at the Laboratory for Manufacturing Systems and Automation, and also coordinating the Masterly project. So Apostolis, the floor is yours.
Thank you very much for the kind introduction, and I hope my screen should be visible now for everyone. My name is Apostolis. I work at the Laboratory for Manufacturing Systems and Automation in the University of Patras in Greece since 2014 as a project manager, and I'm coordinating at this period this EU-funded project called Masterly, as you can see on the screen. I will move on perhaps with a brief overview of who are the big players in this consortium in Masterly. So the project is funded under Horizon Europe program. We started discussions and our work back in 2023. And the project now is on the last phase, the last period of integration. So you can see that we are expected to finish all the work on time in June of this year. But perhaps before going in further details and technical contributions, it makes sense to describe a bit what motivated us as a consortium, even from the proposal phase when we started investigating things around industry. So back then, and during the last years, it is quite noticeable that we have this quick shift of production towards customized products. This is evident in many cases with different kind of challenges, like you can see here. For example, we notice a lot of diversity in different parts or different kind of or types of parts, let's say, like rigid geometries, for example, like the elevators manufacturing case that we will present. We also have, in many cases, very frequent changes in production and the produced parts. So we expect to have shorter life cycles that demand, let's say, this very quick reconfiguration. In other cases, we have the paradigm of small batch and high mix production. So here we need the systems that are flexible enough so they can handle this customization of orders. And finally, we have in many cases complex geometries like flexible materials like big HMIs and screens that you can see here as an example, which is quite difficult to be modeled so we can handle them. That's why we have in Masterly these different components, if I use this term. First of all, we have the intelligent workpiece handling. So we develop in the project different kind of gripping systems like grippers for dexterous handling of both rigid and flexible materials, but also gripping systems like huge cranes for large aeronautics parts. On the same time, we provide this AI-driven control in the gripping systems in the sense that the robots themselves can be cognitive enough to understand what is happening in their surroundings. This covers either the aspect of process perception or environment perception, or especially in this case for interaction, we take into consideration the humans that work closely with the robots. So that's why we also provide this third huge component regarding the user-friendly interfaces. So in the project, we develop both augmented reality applications that support the operator with instructions during assembly tasks, but also other kind of technologies and modules, like, for example, wearables, smartwatches, or IMU sensors that can track both the performance of the operator, but also what is happening in the shop floor in real time. This is also achieved with this kind of platform that we have in Masterly, called Workflow Controller, which is responsible for interfacing all the different technical modules of the project. So this is important also to perform the integration with existing legacy systems, perhaps, that are a bit difficult in production and stay there for a long period, let's say. So in order to implement also all these modules of Mastery, we have some highlights here on the use of AI as enabler. In many cases, this also is linked with efficient interaction between human and robots. From the robot side, first of all, we have this kind of gripper for elevators pilot regarding the dynamic handling of the components, but in the same time, to be able to identify the pose of the object in real time while the grasping is performed. In the center, we have also machine vision techniques. So here we have the possibility to estimate the grasping points of the part and not only their pose, like it's used to be in the state of the art nowadays. So we have challenging parts with different kind of geometries. In the beam picking application of elevators, we have overlaps between parts, so you can understand it is quite challenging to perform a collision-free picking. In the same time, an operator works quite closely with the robot, so we provide here some technologies based on AI, like, for example, the real-time detection of parts while the operators handles the components, but in the same time, be able to recognize the action of the human operator, be aware of the status of the assembly, so you can react as a technical system accordingly. So we have 3 pilot cases in the project, just to give you a brief idea. First of all, we have the elevators pilot from Cleman as an end user, which is focused in a hybrid collaborative assembly system for the assembly of electrical parts in the cabinet of the elevator. Here we have both the AI-driven grasping that I presented earlier, but also we have quite evident the sense of not only interaction, but real collaboration between the human operator and the robot. Secondly, we have with Decathlon, the sportswear production pilot. This is mostly oriented on the handling of flexible parts. So you can understand that this is a huge company, has a lot of different kind of components and products. So it is a huge challenge for them to be able to identify with AI-based vision systems the position of the part so it can perform the correct grasping. Finally, we have also Arnova as an end user, which is the aeronautics pilot. This is a different pilot in the sense we have huge parts, high payload parts like the skin of the aircraft itself. So here the challenge is to provide an autonomous smart crane system that can safely transport the part, the skin, in a specific position in the shop floor where we have an intelligent fixture and gripper, so the operator can work closely and adapt the position for assembly. So here we will have the possibility today to see also a video from our demonstrator in the elevators manufacturing pilot. But perhaps before seeing this video in detail, we should also question ourselves, based on this pilot, what we need in production, the humans or the robots, or can we make it, let's say, more efficiently to work together? So based on this question, usually our end users provided these requirements, this information. They are aware that, of course, operators are preferred because there is this need for sensitivity and complex assembly steps in production. In many cases, also the handling of flexible materials is not so efficiently done by robots nowadays, so they still have to use operators for repetitive activities, which is not so ergonomic, let's say. And of course, it makes sense since operators can quite nicely collaborate and discuss among each other and exchange expertise. On the other hand, we have robots in other cases in assembly lines, and these are preferred, of course, for the high repeatability and precision, but also lower cycle times, which is, of course, quite important for companies nowadays. Perhaps the solution to this problem and what we are trying to propose is to keep both actors and have operators in the center of production. So we can have the precision of robots, but in the same time, we can have operators and propose means of interaction so they can take out the most of its synergy effect, let's say. So here we have also the human-robot interaction as a paradigm, as enabler. So this is a critical aspect for efficient collaboration in shared workspaces. So in the case we have a collaborative robot and an operator, we have different aspects to think about and cover, like assembly instructions, safety considerations, and also either direct or indirect means of interaction, but in the same time to be able to interact with the same production line. So in this sense, we have here a proposition for the future of elevators manufacturing as a paradigm in industry. This is on our facilities in Patras in the Teaching Factory Competence Center. You can see that we have two different areas involved. We have the assembly area where the operator assembles the part in the current state. And we have also the warehouse area. So the suggestion and the future vision, let's say here, is to use a mobile worker, which is able to autonomously navigate in the shop floor, pick the correct components from warehouse, and navigate and provide these components, this bin of components to the assembly area. Then we have a different platform there also to provide proof that all the systems are integrated. It is an RB Kairos platform which also autonomously detects the parts in the bin picking process and provides the assembly, while the operator also completes some other tasks. But to have a better view, you can see also the demonstrator in detail. In the right-hand side, we have the physical execution with the Kairos robot. In the right-hand side, you have the digital twin. Here is the provision of the 60 pose identification and the grasping points with AI vision system. So you can see that inside the bin, we have challenging environment, but the system is able to detect the part, performs the grasp with the gripper that we proposed, and in the same time, we detect the pose in real time in the in-hand manipulation solution. This will help us later on because the robot will try to assemble the part itself, the electrical circuit breaker, in the rail component of the elevator. This is here also an example of the AR application, which is used for interaction. We have specific instructions for the operator about the parts. And here, in the case that we need actual collaboration for screwing, the operator has a specific visualization for manual guidance. So as an operator, you are able to move around the arm of the robot, perform real collaboration safely, and finalize specifically for this process some screwing activities. So as you can understand, this is quite flexible in the sense that the operator can spend some time for his own work, but in the same time react or change parameters of the system and specifically on the robot itself. I think this summarizes my presentation for today. You can also have a look on our website and social media channel. And of course, I will be glad also to discuss further any kind of question later on the roundtable. Thank you very much.
Thank you so much, Apostolis. It's really refreshing to see these high-tech solutions working in, let's say, such a practical, everyday setting like elevator assembly. So thank you so much. And that concludes our case studies. Again, huge thanks to Arash, Roberto, and Apostolis for these insights. So now let's kick off the discussion. And I'm handing over to our moderator, Wael Mohammed, who is the technical coordinator of FORTIS. So Wael, the floor is yours.
Okay, thank you so much, Anne, and thank you for our presenters. Hello, Roberto. It's been like some time since we met. We've been working together in another project, so it's nice to see familiar faces. Yes, basically, as you see, the human is in the center of all of our development. We are trying either to fit the system to understand the human, or try to mimic the human, or try to kind of gain the knowledge from the side of the human. So I will start this maybe panel discussion, and for our attendees, please, I guess you can raise your hand, or you can put your question in the text if you would like to, so we can refer these questions to our panelists. I will kick off with something a little bit generic, but it's always a challenge for us when we work with the human data or with human presence, especially when we are trying to involve them in our development, is how we transfer the knowledge and how we can get the trust from the human that once we move from the laboratory to the factory, how the human in the factory trust our technology, our robots, our transfer of knowledge. So this is a question generic for all of the panelists. So from your experience, how you deal with these challenges?
Yeah. Shall I comment on this perhaps to initiate?
Yeah. You
sure,
can start.
Thank you.
Thank you.
Sure. It is a good point indeed. I mean, it is something that it was already quite noticeable even from the first round of integration in our project, because as you commented, it is quite difficult to not only transfer the knowledge, but retrieve the trust of operators. Operators in many cases are not of the same age or expertise. So you cannot have like a single approach of solving this challenge. In our case, in the elevators manufacturing pilot, they also needed from the end user point of view, and this is what we try to propose, this AR system to be able to adapt in different kind of experience. So for example, they had operators working for years in the factory that know the process very well, but in the case of newcomers that happened during the last years, they had to spend huge time and resources both for training the operators and also for being able to adapt in changes in the orders of production. So with this system, we are trying to minimize, let's say, the effort and the time needed for training new people, but also in the same time transfer the knowledge that is currently written in paper format, in many cases digitally. So new people and newcomers can easily be more familiar with the process, and in the same time, let's say, make it more attractive for them. For performing these activities and gaining the trust of operators, again, there are different kind of solutions, but having a safety in the center is not negotiable for industry. So they want in all of these technological solutions to have some kind of evidence or confirmation, let's say, as a last step by the operators. So even if you propose an AR system with instructions, they still need to be aware, for example, on the safety zones of the robot, since they are working closely. They need to be aware when the robot performs a task, and finally, they need to have the last word, because at the end, it's not only about automation, but it is also about efficient collaboration with existing workers in the factory.
No, indeed. Thank you so much, Obsteris. Is there comment from our colleagues, Roberto, Arash, you would like to add or to contribute to this?
Yeah, I think this was basically all said nicely, and it's always hard to introduce new technologies, especially to the generation which is already working in an industry, and they have their own preferences, way of working. And us engineers, robotics, AI experts come and say, from tomorrow, you're not supposed to do that. You're supposed to do it this way. Work with this robot. And so these steps are slowly being implemented. However, I think there are so many roadblocks. And apart from that, I think the biggest roadblock we have are the regulations that don't really let us to do as. I mean, all the videos that we mentioned, most of the videos that we showed, they're not even, none of these can be easily certifiable. So even if you have the most robust solution, the regulations won't let you to exploit them with that velocity close to a human. You need to put sensors everywhere, and when the person enters the robot's workspace, it should stop. So I think it's not only on the aspect of acceptability and integration and co-design, but also we need to really push on the regulations to make sure that those also catch up with today's needs of industry.
Okay, great. Roberto.
Yeah. My comment is related to trust, which is quite complex also to really well define and face. So from the point of view of what we, let's say, discovered during the project is the exploitation of shared autonomy paradigms. And especially it was very interesting how we developed those methods initially more related to the prosthetic scenario. And then we moved it to also industrial scenarios for programming by demonstration, together with some psychological metrics to measure the embodiment. So we have seen how different shared autonomy methods will directly affect the sense of agency. So for example, if you are programming by means of programming by demonstration some manipulation task with a robotic arm, you can select the shared autonomy method to improve the intuitiveness of your approach, of course, but also to improve the sense of agency. What you are programming is that you perceive as directly related to what you want the robot to make. And therefore, in case you program something that you feel is a consequence of your agency, then we have also very interesting preliminary results. These will affect also your trust in the system, because it is executing something that was strictly related to your willing. So this could be an interesting direction.
Okay, thank you so much. Thank you all. Interesting topic, and from my experience, it is one of the issues that we always try to think, but as it was also mentioned, it's multi-aspect issue. So it's not just us as technology people that we work on. It also requires other aspects, governance and regulations to step in. I will look at the attendees. I guess there is a question to Roberto. So the question is, do you see that the use of force feedback input system, e.g. gloves, would help the robot teaching and automation in general to go faster, like in grasping or picking tasks? Did you try something similar?
Yes. So, yeah, I think that is fundamental to have force feedback in order to close the loop and improve the programming of this kind of tasks, especially grasping tasks that are sometimes little bit less focused than the motion of the manipulator. But in the IntelliMan project, we didn't use the actuated gloves. We are using in general, but in this project we like to investigate the possibility of not using some probably bulky glove in order to give you force feedback. We focused on investigating how we could shape vibrotactile cutaneous feedback to provide information on the grip force. And therefore, in the project, we pushed a lot on this direction, and we found it quite useful. So.
Okay, thank you so much. I don't know, and if we have more time for other questions, other discussion, or how's the schedule?
We have 5 minutes. So if anyone wants to add a question, please feel free.
Okay, I can look at the questions. I don't see question. Maybe I can just shoot another question to our experts in the panel. From your experience and your point of view, what is the bottlenecks that you face into having intuitive, easy interaction similar to the human-to-human interaction? Like if I go to a factory, I put a new machine, a new process, I just take the workers, I teach them. It's very intuitive that communicate with them, that interact with them. What prevents us, and here you can be futuristic if you want also, what prevents us from reaching this intuitive level between robot and human, especially when they are interacting? I will start to the backwards. So Roberto, you first.
Yeah, okay. This is a very interesting question. I will try to go in this direction. So maybe the bottleneck is really in how you embed and then exchange the information within the interfacing channel. And this could be, first of all, bidirectional. And to really go also a little bit futuristic, as you suggested, this should be really radical. So you should be able to exchange both bidirectional information signals, but also power signals. For example, you can command the motors of the robots, but why not? The robots should be able also maybe to send some electrical signals to give some feedback directly in your muscles, for example. But this is to say that we need, from my point of view, more natural interfaces, because since we don't want long learning curves in order to learn how to use interfaces, from my point of view, the only way is to have natural interfaces, which I define as something that you already know how to use because it's directly linked to some natural function that you already have control on your body, for example, and so on. So the communication channel somehow in a large sense.
Okay, great. Thank you so much. Indeed, this is one of the things that we always suffer into, collecting the data and try to kind of like use this data into invoking or actuating the system. Arash, how do you see this?
Yes, very nice question. I think, yeah, I echo what has been said before, but at the same time, I think intuitiveness changes from person to person, but obviously we know what is intuitive should be something that we are using natural ways of communication. But what is challenging is that I think there's no gold standard for human-robot interaction, intuitive human-robot interaction. when it comes to different contexts. So in industry, so in healthcare, you usually use voice or use LLMs nowadays and things like that, sending comments through voice. But this may not be the best option in industry because industrial workplaces are very noisy. There's a lot of background noise, and if you add this, then you will add more to that noise. So we need to find out what's the bottleneck for each level of interaction. But I think that it's probably wrong to get inspiration from humans to say, okay, since humans talk and we need to make sure we always use, language-based communication for intent understanding and things like that. I think we can probably go way beyond that. And I don't have the right answer, but we are, I think, through maybe posture understanding, VLAs, understanding, scene perception. By looking, we can do a lot more than talking, probably.
Okay, thank you. It's a really valid point. Apostolis, sorry if I'm mentioning the name wrongly.
Very, very nice points from the rest of the speakers, and I think we can be really ambitious if we need to solve this challenge. So with the rise of AI, even if we want this or not, this is already used slowly in industry, I would say. More and more end users are getting interested on the use of AI technologies. And I see that one of the core challenges is the explainability from my perspective. So even if you are trying to push things and the state of the art so you can integrate more and more technologies based on AI, what we're missing is also the aspect of explainable AI technologies, in the sense that the solution that you're trying to propose is not working like a black box for engineers or operators on the field. So we can also try to investigate as researchers, let's say, on the field, even more the sense of explaining the decision-making of any kind of AI tool that we are trying to propose.
Okay, great point as well. Thank you all so much. I see Anne is trying to put the time, so.
But I think I see that we have a last question from Yonga that asks, how about the potential of gesture-based intention in human-robot communication?
Anyone would like to answer this question? I have my own opinion on this, but I would like to also from the panelists.
Yeah, if I can just start. Yeah, gesture-based has been there for a long time, and it's a very efficient way of doing that when it comes to very simple gestures. But let's not forget that cultures change the definition of gestures. Yes, in some cultures might mean, if somebody nods like this, you don't really know what it means in some different cultures. So that's not so intuitive to add. But gestures remain one really nice interface between humans and robots in industry. However, it should not be complicated. It should come naturally. So if you need to really use and learn how to use your arm and body to just transmit something to the robot, if it adds complication, this means that it's a wrong path. But natural gestures that we use, like stop, move, or things like that, definitely is a good thing to add. Yeah.
Yeah, I agree with this point. You can transmit very simple messages with some movements, but if you want to make it like independent or disconnected from just the standards, it becomes more and more, in my opinion, not complex, but a long list of possible gestures, and then each one might have meanings and different interpretation. Any other participants who would like to highlight something on this question?
Perhaps I can also add that we need to keep in mind also the same comment like the voice-based commands in industrial fields, which are quite noisy, not only in the sense of audio, but also in the sense of surroundings in the environment. The proposed solution should be able to identify and recognize only the gestures that are needed and not confuse it, let's say, with other people working around like it's used to be in industrial fields, or in the sense that the operator that works closely with the robot should only look at the specific direction, which is not so common for a worker in a complete shift in the day. So this restriction should really be kept in mind while you are trying to propose this mean of interaction.
Yeah, and I agree. And this is where the multimodality come into handy. So you have different types of information coming from different modalities, and then based on what is effective, what is more efficient in the communication you need to use. And in FORTIS project, actually, we are implementing this multimodal aspect where we are trying to rank different modalities, and based on the surrounding status, the human status as well, we try to focus more into which modality to listen and to or to receive the communication, and to send the communication also to the human. Okay. Is there any other comments, questions from our attendees? Okay. If there are no, so I would thank everyone who joined us today. First of all, thanks to our experts in the panel. It's very nice. I was unfortunately busy a little bit with our project visit here, so I joined late in the event, but at least I am honored to have all of you in this panel. And back to you, Anne.
Thank you so much, Wael, for leading the discussion, and a huge thanks to our speakers, Arash, Roberto, and Apostolis, for this very insightful session. Just before you go up, I'm just going to share my screen. I don't know if you can see my screen. Okay.
Yes.
You just have, I'm just sharing here a feedback survey, which will help us to improve our next session. So please feel free to take the QR code. It's only a 2-minute survey, so that we can improve our work. And I really want to thank you again all for participating to the session, and to our speakers. And I wish you a wonderful day. Thank you so much.
Thank you. Have a